Hey Chem 30s, it's Manchak here with another lesson for you. This time we are continuing on with Unit D, or C, pardon me, and we're working our way through organic chemistry. To this point in the unit, we have covered concept C1, which just had us identifying what sort of compounds are considered to be organic compounds and where we might find them in our daily lives. C2 had us dealing with simple alkanes, alkenes, and alkynes, how to name them, how to draw their IUPAC structures correctly, those kinds of things. We moved into concept C3 after that, where we talked about aromatic compounds as well, and then talked about petroleum refining, things like fractional distillation, all of that kind of stuff. Where we moved on to after that, which was last week's lesson, was concepts C4 and C5. C4 had us looking at combustion reactions, particularly incomplete and complete combustion reactions, and C5 had us looking at organic halides, and then we introduced two new chemical reactions that we need to be able to identify: addition and substitution reactions. So that's where we sit right now with the course. So you should be caught up to this point, and you're now moving into concepts C6 and C7. C6 has us looking at alcohols. So we're going to be able to name and draw compounds that are alcohols. In particular, we're going to do alcohols that only have one hydroxyl group, and we'll talk about what a hydroxyl group is shortly. And then we'll have multiple hydroxyl groups in there within reason we'll play around with. We'll talk a little bit about boiling points and solubility again, and that'll come up. And then we're going to continue on into talking about something called elimination reactions and what elimination reactions are and how they work. The name kind of illustrates a bit of what's going on, so you can check that out when we get there. And then we're going to move into C7, and C7 has us looking at two last kinds of, or I guess our third last and our second last kinds of compounds that we're going to explore in this unit. The first one is called a carboxylic acid, and the second one is called an ester. And we'll learn how to draw those and name them according to what IUPAC has laid out for us. Some more of the boiling points and solubility stuff will come into play. We'll still continue to be looking at this whole, derivatives and where these compounds might be coming from. And then we're going to look at our second last kind of reaction in the unit, which is called an esterification reaction, which makes esters. And we'll play around with that. A bonus is that the last concept that we have to cover in this unit is C8, and that'll come up next week, and then we're done with our organic chemistry unit. So just a couple of notes quickly for you as we move forward, things to watch out for and pay attention to as we move through this, this video lesson. First off, with the alcohols and elimination reactions, just pay attention to where the functional group is, and remember what a functional group is. A functional group is part of a compound that identifies it as that kind of compound. So if you see, for example, we talked about, a double bonded compound, a compound that has a double bond between two carbons, that is a functional group telling us it's an alkene, right? If we have a benzene ring, that functional group told us that we are dealing with something that is considered to be aromatic. So watch out for the hydroxyl functional group for alcohols, the COOH, which is the functional group for carboxylic acids, and then the COC, and I'll show you that later, which is the functional group for esters. Then really pay attention to the kinds of reactions that we're dealing with today. The elimination reaction is pretty straightforward. It's no more difficult than a substitution or an addition reaction. However, I find that the esterification reaction can be a little bit more challenging for students. So watch out for that one and do pay attention to how I'm working my way through that. So I also have a couple of videos, and I'm going to take just a couple of minutes to explain these because I think it's important because they're a little bit trickier. So for the two videos, we're going to jump back into Crash Course again because I think he does an excellent job, although he goes by pretty quickly what's going on. So use these maybe as a bit of a review after you've watched the lesson. So you're going to jump into this video called Hydrocarbon Derivatives. It's about 8 minutes, 37 seconds long. You can pay attention through all of it. Really watch out for alcohols, carboxylic acids, esters in there, what they are and how they work. You can ignore aldehydes, ketones, and amines, right? Those are not important. We're not covering them in this course. That'll be your first year university organic chemistry. And then the second one that we'll get into, and this is more of a bit of a review, I find, is this nomenclature or nomenclature, depending on who you talk to, on how to sort of name these things. And he goes pretty deep. Much deeper than we need, but I think it's a pretty good review of what we've been covering so far. Again, going a little bit deeper than we've expected. If you want to, you can stop at about 5 minutes 20 seconds, or if you want to continue on, there's nothing wrong with that. You can continue on. Again, it's a bit of a review. It gives you a little bit more background on IUPAC and where all of this stuff is coming from and why we name these things the way we do. You guys are going to have a worksheet with a key up on the Google Classroom to do for practice. And then I'm going to do a follow-up activity for the activity that we did to start the unit where you guys were constructing your molecular models. We're going to do a follow-up that'll have you working with addition and substitution reactions, organic halides, alcohols, carboxylic acids, and you're going to have to construct an ester as well. So again, I think these activities are great. It is something that we would have absolutely done in class. I would strongly recommend that you guys look at doing those because they are so important for you to understand and really get some playing around with and get that more parts of your brain activated stuff to figure out what we're doing with all of this. So activities coming up then, as usual, you guys will do a practice quiz followed by a summative quiz after you've received my feedback on the practice quiz. So let's jump into now the actual presentation that I want to go through. I'm going to shrink myself down a little bit, and then we will get rolling onto this. I'm hoping this will be a relatively quick lesson, but every time I say that, it never turns out to be. So we're going to start out first with concept C6, which is alcohols and elimination reactions, and then we'll transition our way into C7, and it's kind of nice because they play off of each other a little bit, so I'm happy with that. So first off, I want to talk just really quickly about methanol and ethanol. These are our two most common alcohols that we have in the world, and you've probably come into contact with ethanol at some point, maybe methanol depending on what you've done on the farm or elsewhere in your lives. But they're both more and more being used in gasoline to improve combustion in gasoline. What they do is they add just a little bit extra oxygen to the reaction when they break down, which means that we're going to produce less carbon monoxide, which means that there's less chance of an incomplete combustion reaction and more chance of a complete combustion reaction. I always take a moment to talk about this stuff at the bottom here because I think it's really important to take note with the age that you're at right now, working your way through the last year or two of high school. Be really careful that you understand where your sources of particularly ethanol are coming from. I know a lot of you are into partying and doing those kinds of things. I implore you and I ask you to please be careful to pay attention to where those things are coming from and know where your ethanol is coming from. And the reason why I say this is that there are idiots out there in the world, and I'm not going to pull punches on this one, that think, hey, I'm into university now, I got to party it up every night. Man, I'm running low on money. I think I'm going to go and buy myself or get myself some ethanol from the chemistry lab that I just did. Well, problem with that is that's ridiculously dangerous, okay? Because a lot of those ethanols are cut with methanol, meaning that they have a small amount of methanol in them. Methanol is toxic to our bodies. It can cause you to go blind and it can kill you, even in relatively small amounts. We know that ethanol, which is the alcohol that's in alcoholic beverages, is okay in moderation, but in large amounts, it can also kill you. And what gets really scary is that somebody may grab, instead of grabbing, 70% ethanol, which is often cut with some methanol, they might go and say, oh, I'm going to get really drunk tonight and I'm going to grab 95% ethanol. 95% ethanol is ridiculously strong, and a lot of people are dumb enough to drink it like they would drink regular alcohol, to the point where they wind up ending up in the hospital in serious condition because they've drank too much alcohol and they basically poisoned themselves with alcohol. So please, please, please be cautious with what you're doing with these alcohols. You may think, oh, well, ethanol's just fine. We drink it all the time. Yeah, but it's not. Your body doesn't like it. It metabolizes slowly in your body. And if you're not careful with what you do with it, it can harm you and harm you significantly. So please be aware of that. That is your public service announcement about ethanol and methanol. So now we're going to get into talking about how can we recognize that something is an alcohol, and it is really, really, really simple to recognize. It has a hydroxyl group in it. A hydroxyl group is simply an OH, so an oxygen, and then this little dash here means that it's bound to a carbon, so there's going to be a carbon over here with an oxygen attached to it and a hydrogen attached to that oxygen, which makes sense because each oxygen bonds twice, right? Carbon bonds 4 times, and really we've only been dealing with carbon and hydrogen and then some organic, some halogens right now so far. Now we're adding oxygen into the mix. So please remember, oxygen bonds twice. Not once, not 3 times, but twice as far as we're concerned in this course, okay? So then it's simply from there, guys, it's really simple. It's just simply going back into what we've learned from concept C2. What is the parent chain? If you recognize that something has an OH on it, go to the parent chain right away and say, okay, what's the parent chain? If I have to come up with the name of this, what is the parent chain? Count the longest continuous carbon chain in the alcohol or in the group with the alcohol attached to it, okay? That forms the parent chain or the basis of what we're going to start to name. Then you write the prefix. If it's 4 carbons long, it's a bute. If it's 3 carbons long, it's a prop, right? Add an "an" to the end of that, so it's a propan. Notice that we're not saying propane or anything. We're going propan to indicate that all of the carbon bonds are going to be single bonds. And for us in this class, all of the carbon-carbon bonds will be single bonds. In university, you might move on to something new, but for now, we're not doing double and triple bonds because that's putting 2 functional groups inside of 1 compound. We're only allowed 1 functional group inside the compound, okay? The next bit is the number. You're going to number the carbon chain to give the hydroxyl group or groups the smallest number you can, just like we've done anything else. So we're kind of treating them as a branch again, just like we did with the rest of the compounds back in concept C2 and beyond. And if necessary, we need to add numbers. Okay. So for example, and we're more often going to need numbers in alcohols than we have in other groups. So keep that in mind. Okay. Complete the parent chain then with an "all" at the end. I'm going to put this all together in a second here. Not put this all together, but put this all together. So we know it's an alcohol. So the OL at the end of something tells us that it is an alcohol of some sort. We need to indicate any presence of any substituents or branches that might be located on that. Give the number to those branches if we need to, and then double check to make sure the numbers differentiate this compound from a similar compound. Okay, so those are the steps we're going to go through. I'm going to show you the next slide here. I hope it's not too small on your screen. If it is, I apologize for that. But this just gives us some examples, and we're using line diagrams to indicate these. So I'm just going to go back to my pointer here and get started. So we've got, this is ethanol. So you'll notice that every terminus and every point in an organic compound, a line diagram, is considered to be a carbon. So there's a carbon here and a carbon here. And to this carbon is attached an OH. So right off the bat, we recognize that this is an alcohol. Okay, so this is ethanol. There is only one spot that OH can go. It can go on carbon 1. Okay, if we put it on carbon 2, basically all you've done is flip the compound around 180 degrees. So it's still the same compound. Okay, in this one right here, propanol, or in this case, propan-1-ol. So this is how we're doing the naming for this. I count 3 carbons, 1, 2, 3. But my OH, my hydroxyl group, is attached to this one. So this is the one that we will start counting at. So this will actually be carbon 1, carbon 2, carbon 3. So it is a propan. Since the alcohol is attached to carbon 1, then we'll call it a propan-1-ol. Notice the hyphen in between the N and the 1, and also a hyphen in between the 1 and the "ol" at the end. That's important. You need to have those hyphens in there because this is the locant. This is the place where we know the OH is attached to. Just to be clear, we could, and I'll write it in here just so you guys can see, we could, whoops, go to my pen. We could also have an OH coming off of here instead, okay? It is possible then to have this if we scratch that out. So that would then become not propan-1-ol, but since the OH is coming off of carbon-2, it would be propan-2-ol. So in this case, we have to identify where the hydroxyl group is coming off of in order for us to relate properly what's going on in that compound. Okay? Okay, so then let's move on to this last example. And it is possible for us then to have compounds that, just getting my laser pointer fired up, compounds that have more than one hydroxyl group on them. I'm going to keep it relatively simple for you. We might only have 2 or 3 hydroxyl groups on a compound, but here's how you work with it, okay? So this is, remember, there's not a carbon here. This line right here is just showing that this is a bond attached to an OH, a bond attached to an OH, okay? So this is a 2-carbon compound. And in this case, it is a 2-carbon compound, so it's ethan, right? Because there's a single bond between the 2 carbons. And what's going to change and what's a little bit different than what we've done so far is we keep the E at the end. So it's an ethane, but it's got 2 hydroxyl groups on it. So it's an ethane 1,2 diol, okay? 1,2 because there is a hydroxyl group on carbon 1 and a hydroxyl group on carbon 2. So it's 1,2, and it's a diol because there are 2, di for 2, hydroxyl groups, and ol because they're hydroxyl groups, okay? So we can do suffixes like diol, triol, tetraol, those kinds of things are used if we have multiple hydroxyl groups in a compound, okay? So this is ethane 1,2 diol. If we had a propane molecule with 2 hydroxyl groups on it, then it could be a propane 1,2 diol or a propane 1,3 diol, right? It could be any one of those combinations. I hope that makes sense. The only tricky bit for us here is that we could have 2 or more hydroxyl groups. It's possible, in which case we need to locate them on the carbon compound, on the parent chain, and then remember that we add that E at the end. So instead of it being propan or ethan 1,2 diol, when we have 2 or more, we have to add that E there to make it ethane 1,2 diol, etc., etc. Okay, so I hope that made sense for you. Let's just see if we can sort this one out then together. If you want to try it on your own, you can. I'm going to just continue on along the way here and sort of work my way through this. So I'm going to select a color you can actually see on a white background to start with. Let's go with this blue color here. So let's try to find the longest carbon chain with the alcohol attached to it. So I see 1, 2, 3. I see 1, 2, 3. So this is a 3-carbon chain. To keep this simple for me, I'm going to number this carbon 1, that carbon 2, and that carbon 3. Okay, and what I'm noticing is I see my hydroxyl functional group telling me that this is an alcohol, but I also see 1, 2 branches on this, both coming off of carbon 2. Okay, so then from there, we're going to build from the back to the front, just like we have all the way through on this. So 3 carbons, which means it's a prop, okay, P-R-O-P, and you'll excuse the terrible writing that I'm doing with my mouse. And then I'm going to have to do, there's only single bonds, so we can say propan, okay. Then we're going to locate our hydroxyl group. So it's going to be on carbon 1 because we have to make that as low as possible. So it's a propan 1, and because it's a carboxyl group, it's a propan 1-ol. Don't forget, we still have our 2 branches on here. They are both methyl branches. So I'll write my methyl. Oh, that is horrible. I apologize. Okay, so there's my methyl. There's 2 of them, so it's a dimethyl. I don't know why my mouse is fighting me on writing today. And then they are both coming off of carbon 2. So we're going to call it a 2,2-dimethyl propan 1-ol. Not too shabby, okay? All we're doing is we're just adding little bits onto the stuff that we've learned all the way through the unit so far. So this isn't rocket surgery, as Don Cherry would say. We're just continuing to build on that foundation we built in Concept C2. So I'm going to give you a second here to have a look at this. If you wanted to hit pause, you can. I'm going to drag myself out of the way so you can see the end of the compound. So how would we draw 2,3-dimethyl-butan-2-ol? All right, so I'm going to let you hit pause if you want to, and if you did, great. Hey, welcome back. All right, so let's look at what this might look like. I just have to click myself forward here. There it is. There is our compound. So we're going to start here as we start to construct this. It is a butan, so that means we have to have a 4-carbon chain. Depending on how you want to look at this, let me give you another color here. Depending on how you want to look at this, you could start over here as your carbon 1 and go 1, 2, 3, 4 carbons, or you could start here and go 1, 2, 3, 4 carbons. But anybody see a problem with the way I'm leading you there? Maybe we should number it to make this number as small as possible. So if we do that, we'll number this carbon 1, this carbon 2. Now from there we can go 3 for sure, and let's go 4 up here just to be different. Then what you would have done if you've drawn those 4 carbons already, then the next thing that you want to do is you want to move on to putting your ol on there, your hydroxyl group. So your hydroxyl group is a 2-ol, meaning it's coming off of carbon 2. So there it is right there. And then we have a dimethyl going on. Well, where are those methyls coming off of? Carbon 2 and carbon 3. So we'll add a CH3. There's one of your methyls there, and there's your other methyl there. So we have one coming off of carbon 2 right here, and one coming off of carbon 3 right there. Okay, hope that makes sense for you. Let's move into elimination reactions and try to eliminate this from our knowledge base. Or no, let's not eliminate it. Let's add it to our knowledge base. All right, so elimination reaction is a reaction that involves eliminating atoms. Ooh, there's a good word. Elimination reaction involves eliminating atoms. Okay, I'm okay with that. Let's eliminate atoms. We'll put that in red. I don't know why, but let's do it. And or groups of atoms from an adjacent carbon, from adjacent carbon atoms in an organic molecule. So we call that an elimination reaction. So I kind of like to think of this one as an addition reaction is where we're popping off a couple of small atoms off of either side of a bond. If there's 2 carbons, attached to each other, we're popping off a couple of those in an elimination, or sorry, I had that completely backwards. Rewind and jump back into it. So in an addition reaction, what we're doing is we're popping off a double bond or a triple bond and popping on a couple of atoms to 2 adjacent carbons. In an elimination reaction, we are doing the opposite. We are, like I was describing earlier, popping off a couple of things and then adding a triple or a double bond to something. Okay, so think of it as the opposite of an addition reaction, and I think that will help you out. So these reactions, and the big way to tell that you're dealing with an elimination reaction, okay, is that your products are going to have a double or a triple bond when you're done. So basically we would be going usually from something that is saturated into something that is unsaturated, because we're removing hydrogens or other groups of atoms from 2 adjacent carbons. Okay, so here's some examples of elimination reactions. Cracking is an elimination reaction, and that's the one where we take something like ethane and we run it through a cracking process. And remember, above this arrow, there could be a number of conditions. Maybe it needs to be done in a hot environment. Maybe we need a catalyst, something along those lines. And what we're doing is we're going to pop off a couple of small atoms, in this case, from adjacent molecules. So what we're going to do is we're going to pop off that hydrogen and that hydrogen. Okay, or it could be the ones on the bottom, or it could be one on the top, one on the bottom, doesn't matter. And those are going to end up making, hydrogen when we're done. And then what's going to happen is that leaves a bonding electron here and here. Those 2 bonding electrons will swing down, and they are going to create that double bond that we see there. So we started off with something saturated. We end up with something unsaturated. Okay, and this would be the cracking of ethane. So you're going to end up start out with usually a single reactant. Sometimes we could have another small reactant, but a single organic molecule turning into something that has a double bond in it. That is an elimination reaction. And I should also mention a small diatomic molecule is usually resultant, but not always. Okay. Here's another one, something called dehydration. This basically removes a hydroxyl group and a hydrogen to form water and a double bond. So here we go. We've got ethanol. So here's our two adjacent carbons. What we're going to do is we're going to pop that off. We're going to pop that off, leaving a bonding electron on each of those. Okay, those bonding electrons will come together to make a double bond. And we have an H and an OH left over. Well, two H's and an O makes H2O. So this is dehydration, because hydro meaning water. So we are taking a water molecule out of this organic molecule and making a double bond as a result. Okay, so that's dehydration. For those of you that might remember back to Bio 20, we talked a lot about creation of small or large molecules in our bodies, like proteins from amino acids, or peptides from amino acids, or polysaccharides from smaller things like glucose. All of that was done through dehydration synthesis. So basically elimination reactions. Okay, and if you remember back to Bio 20, I probably said, hey, we're going to talk about this in Chem 30. Here it is. Another kind of elimination is something called a dehydrohalogenation. So this is usually taking place in the presence of a base. So you'll notice that we've got hydroxide as the base there. And we have some sort of an organic halide, in this case chloroethane. And what we're going to do is we're going to break off that and that again, freeing up bonding electrons to make a double bond. And then the Cl is going to just float away by itself. So we've taken the halogen off. So we've dehalogenated it. And this hydrogen is going to join with the water molecule to produce, or to the hydroxide to produce a water molecule when we're done. So we're dehydro, we're taking water out, we're taking out a halogen to make ethene, something that is double bonded. I'm just going to pause for a second and say, why the heck would we want to do this? Well, why the heck would we care about an elimination reaction? I wanted to point a couple of things out. Taking ethanol and turning it into ethene, taking ethane, turning it into ethene, taking chloroethane, turning it into ethene. This is bringing us back to ethene. And if you took the chance to look at back at the beginning of concept C5, I believe it was, there was a little bit of fill in the blank notes you had to do on derivatives and those kinds of things. Ethene is a great molecule for us because it allows us then to go and run an addition reaction to it and make something out of it later on, because it's really easy to break that double bond, get rid of it, and then attach things to it. Or what we're going to see in concept C8 is we can take something with a double bond in it and go ahead and attach more of those things to it to make something called a polymer. And so that's what we're going to be looking at in concept C8, is we'll deal with polymers at that point, and you'll see that we can take those things like with double bonds in them, like ethene or propene, and we can start to stick them together just by breaking the bond and then just tacking them onto each other. So this whole process of doing elimination reactions can lead us into making polymers. Polymers allow us to make plastics. In our bodies, polymers allow us to make things like proteins and polysaccharides, fats, those kinds of things. And we'll see that in the next concept in a big way. A couple of notes about elimination reactions. First, they add a double bond. I'm going to highlight these for you. So they add a double bond. That's your big way for recognizing that you're dealing with an elimination reaction. When we eliminate the target group, whatever it might be. Also note that in order for these reactions to take place, we usually need a catalyst. Like I said, there's got to be something usually over that arrow in our reaction to show that we're having something going on there, and that's usually just to kick off the reaction to make it happen. They're leaving ethanol in a jar on a desk for hours and hours doesn't mean it's going to spontaneously turn into ethane and water. Okay, there might be the possibility that small amounts of it do that. That's unit D that we'll talk about, but for now that's not where we're at. Okay. At this point, I don't expect you to construct your own reaction from scratch. Rather, you should be able to recognize an elimination reaction when you see them and predict the resulting products. Okay, so if you were given just the reactants or a hint that it's going to create a double bond, you should be able to tell me at that point that we're dealing with an elimination reaction. Okay. Now, that's concept C6. I hope that makes sense. If you wanted to hit pause and do some practice on worksheet 4, you can go ahead and do that. If you don't want to hit pause right now and you want to continue on, then hey, we're moving into C7, which has us dealing with carboxylic acids, esters, and the process we call esterification. So a carboxylic acid is an organic acid, okay? We've dealt with inorganic acids before. Inorganic acids like hydrochloric acid, sulfuric acid, hydrobromic acid, they don't have tend to have carbon in them, or in the case of carbonic acid, that carbonate ion is not really considered to be organic. Carboxylic acids still behave like regular inorganic acids, so they still taste sour. They still have a pH of less than 7. They tend to react with water to produce hydrogen ions, right? All of those kinds of things that we would identify, blue litmus paper turns red. They're still going to do all of that stuff. What's really interesting about carboxylic acids is they tend to have a really, really strong odor to them, and very distinct odors. And this is where I would usually, tease to you guys that we would do a lab in class where we'd actually create some esters, which use really stinky acids to create something that's quite smelly but smells kind of good from it. Unfortunately, we can't do that, and I don't have smell-o-vision, so I really can't help you with that. But what I can tell you is that some things like vinegar. Vinegar is probably the one kind of organic acid that you have in your house right now. You know what vinegar smells like. That vinegar is 5%, usually is what you have in your cupboard that we cook with and maybe even clean with. That vinegar smells quite strong. Well, imagine that that's only 5% vinegar, or 5% acetic acid, or better yet, ethanoic acid. If you had 98%, which I have back in the lab at the school, that stuff would knock you out with how strong it is. It's ridiculously strong. I usually have another one handy called butanoic acid, which is 4-carbon carboxylic acid, and it smells like rotten cheese. It is nasty stuff, and if I left the lid off of that for any length of time in the classroom, you would probably smell it over the whole school after a while. It smells that strongly. It's ridiculous. Anyway, carboxylic acids tend to have really often nasty smells to them. They also have something called a carboxyl group on them. And I'm not going to break down I'll break it down briefly here what a carboxyl group is. But basically it is a carbon that has 2 oxygens attached to it. And one of those oxygens is attached to a hydrogen. And in general, and usually I write this on the board, but I will write it with really terrible writing on my computer here. Your carboxyl group is a C, okay, usually attached to another chain, although it could be sitting by itself, and that R just means some other kind of chain. And then it's got an OOH. So that means a double bonded oxygen is attached to it, as well as a single bonded oxygen with a hydrogen attached to that. Okay, so this is your COOH of your carboxyl group. So really it is, if you wanna break it down, it is a hydroxyl group. So that's the oxyl coming off of it. But it's also got a carbonyl group, and that's CARBONYL, and that's this bit right here. Okay, so it's 2 things in there. It's a carbonyl group and a hydroxyl group, making it carboxyl. We're just combining the name together. Like I've talked about just briefly before, these compounds react just like other acids do in a neutralization reaction. So they're gonna behave the same way other acids do. But Due to the presence of both the carbonyl and the hydroxyl groups, the molecules of carboxylic acids are polar, and they form hydrogen bonds with each other, which results in these becoming very soluble in water, and they tend to have much higher melting and boiling points because they have more of those intermolecular forces. And if you haven't reviewed those yet, don't forget that they are London force, which everything has. It is the dipole-dipole force, which only happens with molecules that are polar, and it has the ability to hydrogen bond. And because carboxylic acids have all three of those, and because water has all three of those, that's why they dissolve so well in water. Also, because they have all three of those intermolecular forces, they also hold onto each other much better, raising the boiling points and raising the melting points. Make sense? I hope. Okay. So I've already talked about that, so there's a double up there. To name a carboxylic acid, it is super ridiculously simple. Figure out the parent chain. What is the longest chain of carbons in a row? Is it a meth? Is it an eth? Is it a prop? Is it a bute? Whatever it is. And then we're going to go bute, and then we'll add an an because we're not going to deal with more than one functional group in a compound, okay, as far as naming it or drawing it goes. We'll take the butane, take the E off, and we'll add an oic to the end of it. So if it is 4 carbons long and it's got a carboxyl group at the end of it, we're going to call it a butanoic acid. Okay. Drawing it is very, very simple. The only caveat to it is that the COOH is always attached to the last carbon. So if you're drawing from left to right, put it on your right. Okay. And it's really simple to do. So I've just got some examples, I believe, coming up here to show you, so we'll skip ahead. So these are some common examples. Methanoic acid, meth meaning 1 carbon, also known as formic acid. Ethanoic acid, also known as acetic acid. Citric acid is another one, but it's really complicated. I'll show it to you in a second. You don't have to memorize the names or condensed structural formulas of any polycarboxylic acid. What that means is more than one carboxyl group on the compound. You're going to name and draw ones with only one carboxyl group on them. But you still need to be able to recognize the carboxylic acid functional group, the carboxyl group. So if you see a complex compound that might have a benzene ring and an organic or a halogen on it and a hydroxyl and a carboxyl group, you need to recognize, yeah, there's that carboxyl group over there. That tells me that this has some acidic properties to it. Okay, so here are some examples that I drew up on my handy dandy drawing program. This is methanoic acid, so I'm showing you what's going on here. So imagine, please, that I'm going to get myself a black color here. Imagine, please, that this is a carbon right there, really poorly drawn carbon, and so that carbon has to have 4 bonds on it. So it's going to have 1 bond here with the hydroxyl group, 2 bonds here with the carbonyl group coming off of it, and then there'd actually be another H attached to that carbon. This is ethanoic acid over here. So here is, carbon 1, carbon 2. So there's 2 carbons here, F for 2 carbons. Single bond between the carbons, so it's Fn. But because we see a COOH, then we're dealing with ethanoic acid. Okay, so we've got a carbon double bonded to an oxygen, single bonded to an OH. This is butanoic acid, which I talked about, carbon 1, 2, 3, 4 carbons, with one of those carbons double bonded to oxygen, single bonded to a hydroxyl group. Okay, so this is a butanoic acid. This is citric acid. It's a little bit more complicated. Like I said, what I'd want you to be able to do is look at this and say, oh yeah, there's a carboxyl group. Oh yeah, there's a carboxyl group there and a carboxyl group there. So this is a polycarboxylic acid. We don't need to know how to name it. We would just call it citric acid. Actually, there's a real name for it. We're not going to get into it. What's interesting here is you'll note there's a carbon, 2, 3, 4, 5 carbons, 6 carbons over here. So this is a branch, which is really interesting. And then we got a hydroxyl group coming off of carbon 3 over here. So it's a really complicated compound for us at this point to name. All I want you guys to do is recognize, hey, there's a carboxyl group. Oh yeah, there's another one there. Oh yeah, there's another one there. Oh, and look at that. That is a hydroxyl group as well. Okay, picking out functional groups is important too. So this leads me into talking about esterification reactions and what these are all about. And I'm kind of going to skip over esters for just a second and talk about how we take a carboxylic acid and an alcohol and react them in a particular way to spit out something called an ester. Okay? And why I do this now is because it kind of leads us nicely into talking about esters. So carboxylic acids react with compounds containing hydroxyl groups or alcohols to form what we call an organic salt called an ester. So this is an ester over here. And then some water. So you'll notice that this is kind of an elimination reaction going on here, right? As we're eliminating this and this from each other, and except that we're not really taking and creating a double bond. So let's not consider this to be an elimination reaction. On the surface, it looks like it, but no, it's an esterification reaction. It's some sort of dehydration. It's what we call a condensation reaction. Okay, an esterification is a type of condensation reaction where we're taking two things, sticking them together, and bringing water out when we're done. Okay, so a carboxylic acid combines with another reactant, forming two products. Whoops. One of those products is, in this case, an ester, which we see over here, and the other one is another organic compound called water. Or another compound called water. So we're dealing with what's called a condensation reaction here. One example of a condensation reaction is an esterification. What we're dealing with here, you'll see, is we've got a carboxylic acid and an alcohol, right? There's my carboxylic or my carboxyl group, C, double bonded O, double bonded ox, double bonded the hydroxide, and then we have an alcohol here as well. So we've got carboxylic acid and an alcohol, and what we're doing is we are going to eliminate water from this. So we're going to condense water out of it. We're going to take the OH off of the hydroxyl or the carboxylic acid and the H off of the OH in the alcohol. And what's going to happen, and I'll just draw this with my pen on here for you. What's going to happen is once this is gone, and once this is gone, we free up a bonding electron on that oxygen, we free up a bonding electron on that carbon, and they're going to come together and form a bond between the two. So the bond that you see right here, this bond right there, is that bond that we created there. Okay? This is an ester over here. If you wanted to, you could figure this out to be ethanoic acid, and this is over here as methanol. Okay, and this ester then is going to be something called methyl ethanoate. Okay, methyl space ethanoate. And I'll explain how we got to that in just a second. So esters can be synthesized by the reaction of a carboxylic acid with an alcohol. Esters, but they're found in nature as well, and we actually synthesize some esters in us, and a lot of the fragrances that we get from these esters or from certain things are associated with esters. Really smells, but not necessarily nasty smells like you get in a carboxylic acid, but somehow adding that alcohol to that carboxylic acid and squishing it together makes these really ridiculously good smells. The lab that I normally do would have you making wintergreen, which takes salicylic acid, which is a form of a carboxylic acid, and combining it with methanol in a particular kind of reaction, and it makes methyl salicylate. And methyl salicylate smells like wintergreen. If you think of those lifesaver candies, the white lifesaver candies that takes really strongly of mint, that is what you're smelling. That wintergreen smell is methyl salicylate, and we could recreate that smell in the class if we wanted. What we often do, though, is we can make a plant or a fruit or a flower do that for us, and then we can extract those, or we can synthetically create that in a lab situation as well, if we can figure out what that compound is made up of. There's a functional group for the ester that allows you to identify what the ester is. It's called an ester linkage. I actually prefer to call it, I've written down here it as COO, but I'm actually going to call it a COC. Okay, that's what I use to identify something as an ester. There's a carbon, single bonded to an oxygen, single bonded to another carbon. So it's a COC in there, and I consider that to be an ester linkage, and I can find that in most compounds. There's some, page 439 of your textbook is a great example of some common odors that we can create using esters. So those odors are really interesting. Things from apple to strawberry to pineapple, those kinds of things. Have a look at it, check it out. It's really kind of neat. So here's how we name them. And really the naming is not too difficult as long as you can tell what the alcohol is and what the carboxylic acid is, because basically the name of an ester is a combination of those two things. So looking at our example at the bottom here, what we're dealing with is butanoic acid reacting with ethanol. Okay, and the red here is the OH we're eliminating from the butanoic acid, and the H we're eliminating from the ethanol. That goes and creates water. Then we know that this frees up a bonding electron over here with this carbon, and it frees up a bonding electron over here with this oxygen. And then those two, what's happened on this is I flipped what's in yellow there around. And so we end up with the O, which is this O right here, bonding to this C, that carbon, which is that carbon right there. So this is that COC that I'm looking for. And what the COC, one of those carbons has a double bonded oxygen on it. There is my ester linkage. That's what I'm looking out for. Okay, so this is my ester. So we've created something that's quite a bit longer than the way it started out. So how we name this, how I came up with ethyl butanoate is as follows. The first part of the name comes from the alcohol. Okay, so since this was ethanol, it becomes ethyl. If it was methanol, it would be methyl. If it was propanol, it would be propyl. Make sense? The second part of the name comes from the carboxylic acid. Since this was butanoic acid, we drop the acid and we change the oic to O8. So this becomes butanoate. So this is ethyl from the alcohol, butanoate from the carboxylic acid. Hope that makes sense to you. It's really no more tricky than that. So if this was propane or propanol, pardon me, and this was ethanoic acid, so 2 carbon, then it would be propyl ethanoate. If it was propyl and propanoic acid, it would be propyl propanoate. Okay, really not that tricky doing that. Just have to be able to identify which is the alcohol and which is the carboxylic acid, and then alcohol first, carboxylic acid second, and you've got your name. Just change the suffix for both of those. Okay? All right, so that, I believe, is all I have to do for you for this concept. So we're just a little long. I'm sorry, just shy of 50 minutes. Hope you made it all the way through. If you didn't, I'm sorry. It's good that you took a break. This is just to remind you of the videos. I think now would be a good time to go back and watch these 2 videos. The first one was about 8.5 minutes long. The second one, you could probably stop just after 5 minutes in and you'd be good. The first one, remember, is dealing with identifying those alcohols, carboxylic acids, esters, and a little bit about the properties. You can ignore all of the discussion about aldehydes, ketones, ethers, and amines. We're not covering them in Chem 30. You'll cover that in your first year organic chemistry classes at university. And then the second video is talking a little bit about nomenclature, how we've come up with these names. And so it'll be a nice little review for you to look at things again. Again, you can ignore all of the discussion about aldehydes, ketones, ethers, and amines, and you can ignore the stuff that is double functional group, meaning a double bond with a carboxyl group. Okay, we're gonna ignore that because we don't have to cover that in Chem 30. All right, so that's it for this concept. I hope that you found this informative. I hope this works for you. Please make sure that you reach out to me if you're struggling with anything. Again, I've got an hour of time each day for office hour for you to pop in if you want to and ask questions. Make sure you do the worksheet number 4 as well and activity number 2. I think the activity, if you do anything, do the activity, and you could ignore worksheet number 2 because you're going to, or number 4, pardon me, you'll get the same things out of the activity as I have in the worksheet, but I think the activity is more engaging. So please give that a shot. If you need help with that, let me know. And then move your way on to the practice quiz. Wait for some feedback from me, and then jump into your summative quiz. That's it. Thanks for watching, and we'll talk soon.